All right, to get class started today, you can work on this puzzle. Let me just quick explain how it works here. So you're getting on the metro at your home at stop K, and the metro system will let you get off the train every other stop. So if we are on this line here where K is, you can get off at L and you can get off at B, but you can't get off at N or H because it has to travel two stops before you can get off. So we can't transfer lines until you get to that second stop. So your task is to figure out how you're going to get off at C. Suggestion might be that you work both forward and backwards, partly from home and partly from the market until you can find a path that works. But there is a path that works, and if you would like to do this on your own now, you can pause the video and do it now, or you can wait and try it with a partner later on when you're doing your classwork. So either way is fine, and give it a try. All right, so for the work that we need to do here on page 24, first thing, this is about nonlinear systems. So we're going to start with a system of linear equations just to remind people how this goes. But typically, the purpose of the rest of this lesson will be to work on nonlinear systems. So when you are solving this first set, first off, change the second equation to a plus 3x, just so that the lines aren't parallel. And we're going to try to solve this by graphing first, and then by a couple of other methods as well. So to graph it, we want to get our y-intercept on the line. I think I could do a better job of these lines. So let me get those, get some better lines drawn for you here. But you're going to start with the y-intercept of both lines, and then think about the slope in each case. So if I get the first graph starting at 5, slope of -3, takes me here and then here. And then I can get that line drawn in. And you want to extend the line all the way through the grid. So we'll have it go both directions. And then my second line is going to be at -1, and that one's up 3. And you can tell where the intersection point is already because we had a common point there. But if not, we would just use the lines to figure out where that intersection is. So we get that one on, and then we have our system graphed. So it's evident when we look at this graph that the solution is here at 1, 2. And so that's my coordinate. So a second way to solve it is algebraically. And if you set the two equations equal to each other, since they both say y equals, you get x equals 1. Insert that back into either equation, you get y equals 2. So 1, 2 is the solution algebraically as well. And to do it with a table, you could just have both equations represented from 0 to 5 and insert those x values until you get a common y value. And you can see that the coordinate that matches up again is 1 and 2. So with a linear system, pretty easy to do any of those three methods. All right, on to page 25. And with this part, if you get stuck at any point in time, you can just pause and try to work through it at a slower pace. So we're starting with graphing again. And if I'm trying to graph this first one, think about it in graphing form. There is no h value, but it has been shifted 1 unit up. So my vertex should be at 0, 1. So we'll get that point on there first. And then normally these go 1, 4, 9. But we do have a stretch factor of a half. So we're going to go up a half. Then we're going to go up 2. And then we're going to go up 4.5 from this vertex line. So if I go up a half, that's here. And then I go up 2 from that vertex line, I'm at 3. And go up 4.5 from 1, I'm at 5.5. So there's that part. And then I can just use symmetry over here. And I will tell you ahead of time, writing on a screen, this problem may not be so smooth. Yours is going to be much nicer than mine, I think. That could have been worse. Okay. You want to get it as smooth as possible because remember, we're using a graph to find intersections. So the more accurate your graph is, the better. All right, then I switch over to do my second equation. This one's easier because it's linear. So -1, and then I go up 2, and then I go up 2, and there's the common point. Then I go up 2, and you notice how this line started off below the curve, then it touched the curve, and now it's below the curve again. When that happens, that's called tangent. This line is tangent to the curve, which means it touches exactly once, And that's possible anytime you have a parabola in a line that it could touch in exactly one spot. If it touches in exactly one spot, that means there's only one solution to the system. So the place where it crossed was right here at the coordinate 2, 3. And then we'll just confirm that with a couple of other methods. But if you're not careful with this graph being precise with your points, then that may not appear exactly at 2, 3 like it should. So just be careful when you're doing it by hand. All right, so the algebraic method. So I set the two equations equal to each other. And again, you can do this anytime both equations are in graphing format because you can, if they're both y equals, you can just set them equal. So because there's an x squared and there's an x, I do need everything on one side. So that's my first step. I move the 2x over, becomes negative, add the 1 over, becomes plus 2. This is not very easy to factor because of the 1/2, so I multiply the entire equation by 2. Now it's very simple to factor. It's just going to be x minus 2 and x minus 2. And so both of those give you the same answer, that x equals 2. So then I can go back to either equation. I'm going to take the linear one. So y equals, get a pen here, y equals 2 times 2 minus 1. And so y equals 3. And so again, I get the coordinate 2, 3, just like I did on the graph. Okay, and then the third version. So I need one table for each. This one's 2x minus 1. I'm starting with 0, 1, 2, 3. And if that wasn't enough, if I couldn't find a common coordinate with these, then I would just try some negatives and hopefully land on the best one. You could probably see the limitation of using tables is that if your inputs, if the correct input for the intersection is a decimal version for x, you're never going to find it unless you go by 0.5s or go by 0.1s. So it can be very cumbersome to use a table if we're doing it with non-integer coordinates. All right, so anyway, we put a 0 in for x, we get 1. We put a 1 in for x, we have 1 squared times a half is a half, plus 1 is 1.5. 2 squared is 4, half of that's 2, plus 1 is 3. And if this is going too fast, just go back and insert them all one at a time. 3 squared is 9, half of that is 4.5, plus 1 is 5.5. I'm getting exactly the same values that I had on the graph above. And then over here, if I put in a 0, I get negative 1. Put in a 1, I get 2 minus 1, which is 1. Put in a 2, I get 4 minus 1, which is 3, and then that's my common coordinate. And I would just go one more time to confirm that it in fact does go below the curve again. So you can see negative 1 is lower than 1, 1 is lower than 1.5. Here's where it hits. This is then below again, which tells me that it's tangent, and that's going to be my only answer. So 2, 3 is my only answer. So if I were to have a parabola and a line like this example, it's possible that they cross once like this. It's also possible that they cross twice, and it's possible that they miss altogether and cross 0 times. So you could have any of those three scenarios come up. All right, for the rest of the period, you're working on pages 26 and 29. Page 26 is similar to page 25, so just do it the same way. If you want to do it alone, you can. If you want to do it with a classmate, that's okay too. Page 29, there is an answer key for on this Google Classroom post, so just check it as you go or check it once you're done. But the first 4 are all supposed to be with algebra only, so keep your graphing calculators away and challenge yourself to do those algebraically. Every one of these is an x and a y, so you will need a coordinate. You will need an xy coordinate for your answers. Down here, though, these are all x only for number 2, so you need x only in your answers. And then number 3 is a review problem from a previous unit. All right, so just check your answers on page 29 with the classroom post when you're done.